All right. Okay, let me check. There we go. All right. So, welcome to Statics, Lecture 4. We're now actually going to start doing some statics today. The past few lectures have been sort of recapping stuff that you should have seen in other classes to some degree. I mean, we did units and dimensional analysis and covered the requisite mathematics and trigonometric skills necessary. So, you know, your homework 1.1, in terms of the logistics, homework 1.1 is graded, although the system sort of automatically graded that one. The solution is available, and homework 1.2 was due today. Now, homework 2.1, it's assigned and it's due Wednesday. This is going to be, I guess, a more classic homework assignment in terms of delivery, and this is going to be how the assignments are handled from here on out. So instead of them being like quizzes, like like we've done before, this one's going to be an actual homework assignment where you do the problem on paper, turn it in as a scanned PDF via CAM scanner. On lecture 1 of the notes, I had a little link where there's a little YouTube video that I recorded where it shows you step by step how to actually take like a written assignment and turn it into a submittable PDF on Blackboard. And so I'll send that out on Teams later today so that you just have that, so it's a little bit more convenient. I do have the attendance grades up to date as of today. One thing I do want to mention about the QR code scan, if you missed the scan, let me know. Or if you had some issues scanning it, come up to see me after class. There was a couple people during the Friday lecture, which I think what happened is they, like a student that was in here got the URL link and sent it to another student, and it sort of makes me think that maybe that student wasn't here. Maybe they were, playing Fortnite or Among Us or something during class. They might have innocently been here and just missed the link. If you missed the link, that's fine. But the signatures are time-stamped, so when I have like a student or two that signed it like 4 minutes after everybody else, after the QR code's down, it's like, well, how'd they get the link? So I'm usually pretty easy to get along with. If you miss the code, let me know, and I'll mark you down. That's not an issue at all. Attendance isn't that big of a component of the grade, but it is important. So I'm also pretty easygoing. If you have a scenario where you can't be here, let me know, and I will more often than not excuse that absence. That's not a big deal. Okay, let's start getting into statics today. We're going to begin our discussion in this class with the first topic, which is statics of particles. And really, that's just a fancy way of introducing you to one of the two primary components of static equilibrium, and that's dealing with forces. Our second main topic will be dealing with moments, but that'll become clear as we get into this. Okay, I've sort of introduced this idea of vectors a little bit, but I kind of want to do it formally today because this is when we're going to start using it. I have mentioned throughout the semester that if you just look at the cover of your textbook, the cover of the textbook, the title of it is Vector Mechanics for Engineers. Vectors are a pretty important concept in this course. So I want you to understand what a vector is and why we're talking about it. Okay? So on day 1, we talked about physics, we talked about mechanics, and sort of set the stage for why the heck we're even in this room. And so mechanics, can generally be defined as the study of forces. And in order to define a force, we really need to define two quantities: a magnitude and a direction. Okay? Now, in mathematics, we have sort of two objects that we utilize. I use the term objects because I think it's probably the best noun I can think of. But we have two objects that we use in mathematics that can express this. We have the term scalar and the term vector. Okay? Now, scalars are mathematical expressions that only contain magnitude, just a number. Okay? And so there are some examples of this in the real world. Volume is a scalar. Temperature is a scalar. Like temperature. Temperature doesn't have a direction. Like how hot is it? It's not 96 degrees northeast. It's just 96 degrees. It's just a value, okay? Mass has a magnitude, but not a direction, volume, temperature, etc. Area, things like that. However, we do also need a mathematical object that contains both magnitude and direction, and we call that a vector, okay? And there are some real-world examples of this. Velocity, acceleration, forces, okay? One common force that we deal with in engineering is weight, okay? Weight is a vector, okay? Because, for example, take me. I have a certain magnitude to my weight, however much the scale says, and then there is a direction. What direction is my weight pointing? Straight down, right? That's the direction of vectors due to self-weight. Straight down, okay? So that's a magnitude and a direction. Separate from mass, because mass is just a measure of the number of atoms and molecules in my body. It's just a scalar, but weight has a magnitude and a direction. Okay, so velocity, acceleration, forces. To go back to the weather example, temperature is a scalar because it's just a magnitude, but wind, okay? Wind would be a vector, right? Because what's the wind today? Well, it's 30 miles per hour south by southwest or whatever, that way, right? So it's a magnitude and a direction. Now, if you open your textbook and start perusing through the pages, you're going to start seeing a bunch of letters show up in bold letters, okay? And if you remember on, I think it was day 2, lecture 2, when we talked about Newton's laws of motions and velocity and acceleration, I said that some letters are bolded, and they're bolded for a reason, if you remember that. Well, in our textbook and just in mathematics in general, we tend to denote vectors with bold letters, okay? Whenever you're opening a textbook and you see a bunch of formulas and equations and some of the letters are bold, that's because it's a vector, okay? So in your textbook, vectors are going to be bold. That's kind of tough to write by hand. Like, you know, there's vector V. Am I going to do this for the V? Like, really color it in. That's the vector. Now, that's kind of difficult. So whenever I draw vectors on the board, or the OneNote, I should say, I'm going to either draw them with a little arrow over the letter, or I'm going to draw them with like a little hat over it. So if you ever see me draw a symbol with an arrow or a hat over it, that's usually what I'm indicating is that that's a vector. Later on, we will utilize a certain vector notation called IJK. If you've had any later calculus courses like Calc 2, Calc 3, you've probably seen IJK before. If not, you're going to get a crash course in it here. And I'll usually call it I hat, J hat, K hat, just for simplicity. Vectors are generally defined by 3 data points. So obviously there's the magnitude, the direction, and we usually like to draw it with a point of application or an origin. When we first start dealing with vectors, we tend to draw them to scale because of some of the mathematical operations that go along with that. And that'll become clear today why the scale might matter. So, for example, this might be a representation of a vector. So we have a point of application. We have 10 pounds, and we're yanking it at 30 degrees from the horizontal. So that might be a representation of a vector. Vectors, in terms of the math, you can multiply a vector by a scalar to change their magnitude. So if I have, for example, this 10 pounds at 30 degrees, and I multiply it by 2, it'll retain its direction, but it'll just be 20 pounds. So you can multiply a vector by a scalar to change its magnitude. That won't change its direction, though. However, if you do multiply a vector by a negative number, it maintains the same line of action. That term line of action will become important later. But it'll just flip its direction on the opposite way. So if we consider some vector P, and notice here I'm drawing or typing P with a bold letter, if you multiply it by 1.5, that'll increase its magnitude by 50%. If you multiply it by -2, its magnitude will double, but it'll just flip, you know. So it's along the same line of action, just, I guess, reverses its direction. So I say that scalars don't change the direction, I guess, with one addendum to that you can just flip it along that line of action. If you multiply a vector by 0, technically that doesn't change its direction, but it has no magnitude, so it's not really doing anything. So far, so good? Okay. Now, our first task, and really the whole purpose of this first big topic in statics, and so your first exam is going to be primarily focused on this task, is adding vectors together, okay? So if we have a point where we have a series of vectors all being applied, or a point where there's a series of forces being applied, that's sort of our task, is to try and add those together. Now, if we have vectors that meet at a common point, we call that a particle. So that's why this first topic of the class is called statics of particles. Really, another name for this scenario is a concurrent force system. I probably won't use that term very much, but I like it because it differentiates between our second topic, which is a non-concurrent force system. Really, all I'm saying is that for this first part of the class, anytime we're adding vectors together, we're assuming that those vectors all meet at a common point. Hence why concurrent force system. When the vectors don't meet at a common point, that would be referring to a non-concurrent force system, and that's where we have to introduce the second big tool in statics, which is a moment. Okay, because in order for a system to achieve static equilibrium, not only must the sum of forces on that system be 0, but the sum of moments must be 0 as well. But that's stuff for later. All right, so what we're going to do in here is we're going to start with learning how to add 2 vectors, and then we'll progress to adding 3 vectors, 4 vectors, 7 vectors, n vectors, okay? And so we're going to start with sort of a trig-based approach for adding 2 vectors, and I think that this stuff is good to sort of shake off the rust of all that trig stuff that you haven't done for a while, but it'll become pretty clear that if I wanted to add 7 vectors together, that using a graphical or a trigonometric approach is going to kind of be nuts. So that's why we'll break out the IJK notation. Now, vectors that are along the same orientation can be added by just combining their magnitude. So it's sort of, I've got a couple of examples here that kind of illustrate the reality of what I'm talking about here. If you and some friends are trying to get a car moving, along the side of the road, and you're all 3 of you, or however many friends, are all pushing in the same direction, if this friend is pushing with 50 pounds, this one 60, this one 80, and you want to determine, well, what is the total resultant, what is the total magnitude, because they're all pushing in the same direction, you can just add all those up because they're all along the same orientation. So vectors that are along the same orientation can be added by just combining their magnitude. Also, kind of the idea with what's going on here with the tug of war exercise. So we have a bunch of folks in blue and a bunch of folks in purple, and they're yanking on this rope trying to win the tug of war. If they're not moving, then the resultant force is on that system is going to be 0. That doesn't mean that there isn't tension in the rope, but if they're yanking with 600 pounds this way, and they're yanking with 600 pounds, in the equal and opposite direction, the rope isn't moving. The sum of forces along the system is 0. Again, the rope has a fair amount of force inside, but it doesn't mean the system is moving. So this orientation is referred to as the line of action of the force. So the path in which the force is moving, that line of action and understanding what that means is going to be pretty important throughout the semester. We'll take it slow, but we'll progress into that. Now, from a graphical perspective, and by definition, vectors add according to what I'm calling the Law of Parallelograms, which is basically just sort of a trigonometric or graphical approach to adding vectors. In other words, what we can do is we can arrange vectors in sort of a tip-to-tail fashion, and we can sum those individual vectors by just drawing the resultant between beginning to end. So the easiest way to explain that is right here. Let's say I have a particle, a point, and I have 2 loads applied, load P and load Q. What I can do is I can stick those vectors tip to tail, move one here and one there, the tip of P to the tail of Q, and so I can say that the resultant vector, and that term resultant is going to be kind of important later, is basically just from the beginning to end. Now, the reason why we're calling it the law of parallelograms, and this is going to be kind of important later, is vector addition is what's called commutative, which means it doesn't matter what order that you do this in. For example, what I'm doing here is I'm sticking the vector q on the end of the vector p. If I stand the vector p on the end of the vector q and say we'll start off with q here, we'll say this is q, and then put vector p here, assuming that I draw that to scale. And notice how I tried to put my little arrow on the top of those vectors. Basically what I'm saying is that p plus q is the same thing as q plus p. And my artwork there I know is horrible. I'm going to show you a little bit of a better way of visualizing it using AutoCAD, because I'm much better at drawing things to scale in AutoCAD than I am by hand. But the idea is that the sum of the individual vectors can be represented as a single vector between the tail of the first and the tip of the last one. And so this p plus q, basically instead of dealing with two vectors, I can say that these two vectors can be represented by just this single one here. And that single one there is very important. We call that the resultant. And so the resultant and understanding how to compute that is going to be one of our big tasks here. And same thing with multiple vectors. We can do p plus q plus s plus however many vectors there. We just stack those on a tip-to-tail fashion, and then the resultant is from the tail of the first vector to the tip of the last vector. So again, vector addition is commutative. It doesn't matter the order of operation. You can add vectors in any order that you want, and it works. So again, if I have this image here and I wanted to determine the resultant of p, q, and s, I could do p plus q plus s. I could do p plus s plus q. I could do s plus p plus q. I could do it in any order, and it wouldn't matter. I would still get the same answer at the end of the day. So in order to add vectors together, we're going to need to dust off our trig skills, and I've got a good example to do that. I'm a numbers guy. I think all these symbols and all this alphabet soup can be a little bit of a difficult way to understand this. So I want to do this graphically, and I want to do this trigonometrically. We've got here like a little hook bolt, a little bolt with a hook on the end of it. And let's say I've got two cables attached to that hook. I've got a 900 Newton, one cable has 900 Newtons on it, and it's yanking about 30 degrees from the horizontal. And then I got 600 Newtons, and it's yanking about 75 degrees from the horizontal. Okay, and what I want to do is I want to say, okay, I've got two cables here. If I wanted to replace those two cables with just one cable, but that has the same effect, I need to know what's the force in that one cable, and I need to know what the orientation of that one cable is. So the idea is to take this system of two forces and resolve it into a system of one force. Okay, and so the goal is going to be to compute the resultant. And so we're going to do it two ways. The first way is going to be the trig approach. I'm going to do it in an opposite order because I want to break out the AutoCAD to show you how this works for the second approach. All right, does everybody have this? I'm going to pull up. Excuse me, goodness. I'm going to pull up the class notebook here in a bit. It also has this image here, so if you miss something, you're going to see it here in a second. Oh, I don't want to keep my ink annotations. All right. So here we go. I have it right here. Okay, I noticed that there were some folks sort of adding or drawing this out, so I'll give you a sec and then we'll go through the problem. We're in no hurry. We got plenty of time to do this. And this example is going to involve some geometry, some trig rules and whatnot. So please, if you have questions, ask, because what I don't want is for you to not follow along because there were some questions and whatnot that you had. Please, if you have questions, ask. All right, everybody good? Okay, so what we're going to do here is we're going to recognize that what we have is we have this point here. We'll call this point, I don't know, A. It doesn't really matter. Okay, and we have two forces applied. A 600 Newton force and a 900 Newton force. Okay, so we've got 600 newtons and we've got 900 newtons. Okay, Now, if you remember, what we can do is we can stick those vectors on top of one another in that tip-to-tail fashion. So what I'm going to do is I'm going to do that, and I'm going to do it like this. I'm going to say, let's do the 900 newtons, and then we'll stick the 600 newton vector on top of it like that. Again, that tip-to-tail fashion. And the idea is to try and figure out what is going on with that resultant. What's going on with that resultant? Okay, let's do a little bit of more clean images, if you will. Let me expand this a little bit. This is going to require a little bit of artwork on my end. So let's start off here. So we'll draw myself a small little coordinate system right there. And I'm going to try and draw this to scale, okay? Which, by the way, something that's worth mentioning that might be a valuable addition to your backpacks. In addition to calculators, might not be a bad idea to bring straight edge with you because we're going to be drawing a lot of pictures and a lot of images in here, and it makes life a little easier. Okay, so let's start off with this 900 Newton force. So let's draw that, I don't know, like that. And so this is 900 newtons, okay? Now, let's see if you all are paying attention. What is that angle right there? 30 degrees, okay. All right, now what I'm going to do is I'm going to draw another little coordinate system right here, because this is going to be kind of valuable. All right, we're going to draw another vector, 600 newtons. Now, a couple of points. See how long I drew the 900 newtons, and then see how kind of short I drew the 600? I'm trying to retain the scale. The 900 Newton vector I'm going to draw longer because it has a larger magnitude, okay? It has more oomph to it, okay? So I'm literally drawing it longer. The 600 Newton vector doesn't have as much force on it. Now, let's see if you all are paying attention, okay? First off, what's this angle? This one right here. 30 degrees, right? Remember, I had mentioned during the last lecture that if you ever have two lines, right, and they are cut by a transversal, right, that this angle, this angle, this angle, and this angle are all the same. And so we have parallel lines cut by a transversal. These two are the same. So far, so good? Now, let's see if we're paying attention. What is that angle right here? 75 degrees. It's not 45, it's 75. Because we're measuring, when this angle right here is that angle right there, right? From the horizontal all the way to the angle in question. So, let me erase that because that got kind of sloppy. So this is 75 degrees, okay? So, here's the kicker. What is that angle?
105.
105. Now, how'd you get that? There's supplementary angles, right? So, think. Horizontal to horizontal, right? That entire angle is 180 degrees. So if this is 75, that makes that 105. Does that make sense? So 105 degrees. So what I can then do is I can now sort of replace this diagram with one that maybe is a little bit less convoluted. This is 900 newtons. This is 600 newtons. And now, what is the angle between these two vectors? 135. Right? Because it's 30 degrees from the 900 to the horizontal, and then another 105 to this. And so now we can start looking at, oh, I can do better than that. Sorry. Oh. Now we can start looking at the result, and I'll just draw that as a solid line. And so what I want to do is I want to determine two things, the magnitude and the direction, okay? So if I want to determine the magnitude and the direction from a triangle perspective, from a trig perspective, what I really want to know is how long is that? And I want to know that angle, okay? I want to know that angle. Now, let's look at this triangle. If you remember, I had said during the last lecture, we have these two tools for triangles that are not right triangles, that are not 90 degrees. We have the law of sines and the law of cosines. And there were scenarios when you would use one versus the other, when one is more useful or more beneficial, okay? So if you look at this triangle, we've got three knowns, we have three unknown quantities. If I was starting out, which law would I use first, the law of sines or the law of cosines? You may remember. Cosines. Why did you say cosines? That's a fair observation. Another observation is the law of cosines works very well when the three quantities are lumped on one side. Like I have this angle and I know these two and I want to find the other one. Make sense? That's a great point. All right. Now, what we want to find is, so we're going to call this vector R. Oh, we're going to call this vector R. Vector R for the resultant. Okay. What we need to find first is the magnitude of R. Okay. Now, just so you're aware, this is something that you're going to start to see me do here and there throughout the course, is some notation. I'm going to put this notation up here. The magnitude of some vector R is sometimes expressed like this. Like you'll put the vector R with absolute value signs in front of it. That's a common notation for magnitude. Another way is to literally just write the letter R with no vector symbol, because the magnitude of a vector is just a scalar, okay? That's just a number, right? Remember, scalars have magnitude, vectors have magnitude and direction, okay? All right, so let's look at the magnitude of R, okay? This is what I propose. I propose that R squared equals 900 newtons squared plus 600 newtons squared minus 2 900 newtons, 600 newtons, cosine 135 degrees. Now, I'm sure some of you are like, whoa, where did he come up with that? He just put some stuff on the screen and went, just came out of nowhere. when you have a triangle, and this is A, this is B, this is C, and that's angle A squared equals B squared plus C squared minus 2BC cosine A. It's just the law of cosines. That's all that is. So all I did is the law of cosines to determine the length of this vector. That's it. So therefore, and by the way, if you ever see me write these little 3 dots, like a triangle of dots, that's just shorthand for the term therefore. R is the square root of all of that. Here we go. Let me move this out of the way, this little diagram here. I got to say, that is something I kind of like, that I can't do that on a chalkboard. All right. Does somebody have a value for R, the magnitude? And we'll say to 2 decimal places. 1390.57. Okay, first off, what are the units on that? Newtons. Okay. Do I have a second on that value? Good. All right. That's right. Is there anybody in here that is having trouble getting that? The first thing I'll tell you is that if you are having trouble, check and make sure that your calculator is in degree mode. Because if you're taking the cosine of 135 and it's in radian mode, your calculator will give you an answer and it won't match this. Make sure that you don't forget your exponents. And what you might want to do is just do all of the stuff under the root first and then just take the root of your answer. But I'm going to give everybody a sec because I want to make sure that you can get this. Yes?
Can I ask what the original question was first?
Oh. No, you're fine. Let me zoom up a little bit. We got time. You good?
Thanks.
Oh, no problem, no problem. Again, whether it's loans, scholarships, your parents, somebody's putting cash money for you to be in here, so get your money's worth. Everybody good? All right. Now, what I want now is the orientation, okay? The direction of R. So we'll put that over here, direction of R. Okay? In order to get the direction of R, what I'm interested in is this angle, okay? I'm going to break out some Greek alphabet for you. We're going to call this angle alpha. Now, I don't really care how you solve it at this point because you've got the law of sines, you've got the law of cosines, you've got tools that you can use. It doesn't really matter. I don't know about you, but I usually try and revert to the law of sines whenever possible just because the formula is a lot smaller. There's a lot less stuff going on. I find it easier. So, you know what? If it's okay, I'm going to erase this. This is getting in my way. So, in order to determine the direction of R, what I'm going to do is I'm going to need to use opposites, right? So the sine of alpha is to 600 as the sine of 135 is to the magnitude of R, right? Make sense? Because that's what I'm interested in. So let's write that out. So the sine of alpha is to 600 as the sine of 135. is to 1390.57. Are you okay with that? Is that going too fast? Everybody good? So you should be able to solve this, I would think, pretty easily, right? I can multiply both sides by 600. And so I could get the sine of alpha. Let's do that first. Let's not rush. What's the sine of alpha equal? So sine of 135 times 600 over that. And let's be a little accurate. Let's go like 4 decimal places so we get so we all kind of get the same answer. We'll do the inverse sine later. Anybody got a value for this part right here? 0.3051. Do I have a second on that?
Yeah.
And so therefore, alpha, here I'm going to scroll down a little bit, my apologies, is the inverse sine of 0.3051, which is what? 17.76 degrees, right? And a second on that? Good. All right. Now let's see if you all are paying attention, right? So I have an expression for magnitude, and I have an expression for direction. So therefore, if I wanted to describe vector r, would this be correct?
No.
Hold on. Well, hold on. I didn't even write it. You're spoiling my thunder, though. So 1390.57 degrees, and we'll say at an angle of 17.76 degrees. Is that correct? Why? Whoever said that, I'm asking.
Because it's not the right direction, because you have to take into account the 30 degrees, such as 900 meters.
That's exactly right. Let's go back to our images up here, right? Let's do this. Here's our coordinate system, right? That angle right there was 30 degrees. I know my art skills are horrible and it's way off scale. But that's 30 degrees, right? All that alpha is just this angle. From the horizontal, it's not 17.76 degrees. It's 47.76 degrees. From the horizontal, we go up 30 degrees to get to this, and then another 17.76 to get to our resultant. Does that make sense? Everybody okay with that? So, what's our answer? Let's be clear. What's our answer to this problem? This problem said determine the resultant vector. What are the two quantities that describe a vector? What was it? Magnitude and direction. So here we have a vector, right? This is magnitude. This is direction. And that was commotion on the floor above us. All right. That's the answer. Now, we're not completely done because we have to do the graphical approach here in a bit. But I'm going to stop for a sec and see if anybody has any questions. Everybody good? Now, here's the thing. This is all doing it using a little bit of trig, but to be clear, vector addition, if you remember me saying this earlier, follows the law of parallelograms, follows, graphical approaches of drawing this to scale. Now here's the thing. My ability to draw things to scale, just right here, is pretty horrible. My art skills are atrocious. Look at this. I mean, here's these two angles. That's 30 degrees, that's 17 degrees, and the 17-degree angle looks bigger. I'm just not that good. Well, what I am good at, though, is breaking out a little bit of AutoCAD. So my graphical approach, I'm going to do this in AutoCAD. So just to show you that this works. Okay? So this is AutoCAD. I imagine most of you have used this, right? Or MicroStation, something similar. It doesn't matter. All right? What I'm going to do is I'm going to draw these vectors as lines in AutoCAD. And then we're going to look at the resultant and see what happens. So let me zoom out a little bit so you can kind of see. So, man, the relief on this is pretty horrible. But there's my origin. This is X and Y. There's my origin. So I'm going to draw a line by typing the word line. I know it's very creative. And so the first thing it's asking to do is specify the first point. So I'm going to say 0, 0. Okay, and so there we go. So we can see I'm drawing that line from the origin. Okay, now let's go back to that first vector. What was that first vector? It was a magnitude of what? 900. And from the horizontal, what was that measurement? 30 degrees. Okay, so does anybody remember how you do that in AutoCAD? Does anybody remember that little keyboard trick? So you type at, like your at symbol, 900, and then you type the less than symbol, 30. All right, I'm going to hit escape, and then I'm going to zoom out a bit. Okay, so there's my first vector, right? Starts at 0, 0. It has a length of 900, and it is oriented at an angle 30 degrees from the horizontal, right? This, what I'm doing right here, this would be the equivalent of me breaking out the protractor and the ruler and actually trying to draw this to scale, right? I just don't have that here on the screen, so that's why we're doing it in AutoCAD. So at 900, less than 30. That's the keyboard shortcut there. Now let's draw another line. All right? And what I'm going to do is I'm going to do that tip to tail fashion. So we're going to draw a line there. So now I have another vector. What was the magnitude of that second vector? 600. Now from the horizontal, what was the orientation of that vector? 75 degrees. At 600, less than 75. All right. That is a lot better than what I could draw by hand. And to be clear, what we're seeing with these two vectors is just this drawn a lot better, right? So this is the 900 Newton vector. That's the 600 Newton vector. And so if I go back to AutoCAD, what we were interested in the whole time is drawing a line from here to here. That's what we're interested in. Let's make that, I don't know, yellow. It's my daughter's favorite color is yellow. So, all right, that's the resultant, right? So that's great. That's the AutoCAD picture. What am I going to do with that? Let's go into AutoCAD and let's type in the word properties. When you type in the word properties, you get a little dialog box here. What I'm then going to do is select that line. What do we see here? Look right here. I don't know. It might be a little difficult to read. What's the length? 1390.57, right? What's the angle? 48 degrees, right? What did we get? 47.76? So the idea is that you have another approach. Another approach would be to break out the protractor, break out the ruler, and actually draw this thing to scale. It obviously is not going to be as accurate as doing the calculations, but that's the nice thing about AutoCAD. AutoCAD is that accurate. Like, you're actually drawing the data, and it will give you the result. So it will operate in that same fashion. The other thing that's worth mentioning is you can actually kind of visibly see the, let me close this. You can visibly see that the order of operations doesn't matter. Watch this. Let's draw a line. All right. Now let's do it the other way. Let's do at 600 less than 75. Let's do the first vector. Now let's do the second one. At 900 less than 30. It doesn't matter what order it is, right? Vector 1 plus vector 2 is the same thing as vector 2 plus vector 1 because we get the same resultant. I'm going to stop for a sec. I want to see if anybody has any questions about this. Keep in mind, all this is being recorded, so if you, like, what commands did he use? You can see it right there. Also, if you're a Marshall student, you can start an Autodesk education account with your EDU email address, and you can download AutoCAD for free. So yeah. Any questions? So if you understood this, you get the at-home game. You get an assignment tonight where there's a problem in the textbook. It's a similar problem. There's a point that has two forces on it. Determine magnitude and direction. Okay? That's the goal for the homework tonight. If you understood this, then the homework tonight, or the homework due Wednesday, should be no problem. Anything else? That's all I got, everybody. I will see you all on Wednesday.